The logic of imaging has been reimagined by scientists, leading to a revolutionary transformation in microscopy. Greetings, everyone. Today, we will be delving into an exciting subject regarding the groundbreaking advancements made by scientists in the field of microscopy. They have completely transformed the way we approach imaging by reimagining its fundamental principles, leading to the development of a revolutionary technique that minimizes radiation damage to samples. Through the creation of an event-based detection system, these scientists have successfully implemented a method that allows them to precisely halt the electron beam at its peak efficiency during imaging, thereby requiring fewer electrons to generate high-quality images. This remarkable breakthrough, known as tempo stem, incorporates a beam blanker that effectively controls the electron beam, resulting in enhanced microscope capabilities and significantly reduced damage to samples. Without further delay, let us dive into our captivating discussion. At present, the process of imaging with scanning transmission electron microscopes, STEMs, involves the precise directing of a concentrated stream of electrons across samples, gradually constructing images by scanning point by point. Traditionally, the beam comes to a halt at each point for a predetermined duration, allowing the accumulation of signals. Similar to traditional cameras that utilize photographic film, this method produces images with a consistent exposure time throughout, regardless of the characteristics of the image area. Electrons continuously bombard the sample until the designated dwell time for each pixel is complete. Although the conventional approach is straightforward to execute, there is a risk of excessive harmful irradiation that could potentially result in the alteration or destruction of the sample. In a groundbreaking approach, the new technique completely transforms the conventional method of imaging by re-evaluating its fundamental principles. Rather than observing for a set duration and quantifying the number of events detected as electrons scatter across the sample to form an image, the team devised a detection system based on events, measuring the fluctuating time required to detect a specific number of these events. The two methods yield comparable image contrast in terms of detection rate. But the underlying mathematical theory of the new approach reveals a key insight. The initial detection of an electron at each probed location contributes significantly to image construction, whereas subsequent electron impacts at the same point offer diminishing informational gains. Furthermore, every electron that interacts with the specimen carries an equal risk of causing damage. In essence, this new approach allows for the ability to turn off the lighting precisely at the pinnacle of imaging effectiveness, resulting in the requirement of fewer electrons to construct an image of comparable or superior caliber. However, a mere theory is insufficient to achieve a mode of reduced radiation. In order to accomplish this, the research team has obtained a patent for a technology called tempo stem in collaboration with Ideas Limited. This innovative technology incorporates a sophisticated beam blanker that effectively blocks the beam after achieving the desired level of precision at each measurement point within the sample. Leading the research team behind the recently published article in the prestigious international journal Science is Dr. Lewis Jones, who holds the positions of Usher Assistant Professor in Trinity College Dublin School of Physics, Royal Society Science Foundation Ireland University Research Fellow, and funded investigator in AMBER, the SFI Centre for Advanced Materials and Bioengineering Research. In an exhilarating manner, he expressed that the fusion of two cutting-edge technologies results in a significant advancement in the microscope's functionalities. The unprecedented achievement lies in the microscopist's newfound capability to instantaneously activate or deactivate the electron beam in response to real-time occurrences, akin to a blank or shutter mechanism accomplished within nanoseconds. By implementing our approach, we are able to decrease the required radiation dosage for generating high-quality images, eliminate the surplus dose that was yielding diminishing returns, and prevent any unnecessary harm to the sample. The lead researcher, Dr. John Peters from Trinity, has taken the helm as the primary contributor to this study. According to Dr. Peters, electrons, despite their seemingly harmless nature in terms of radiation, have proven to be quite destructive when directed towards minuscule biological samples at velocities reaching 75% of the speed of light. It comes as no shock, then, that these samples suffer significant damage. This poses a substantial challenge in the field of microscopy, as the resulting images may be rendered useless or, even worse, misleading. Clearly, this presents a serious predicament when it comes to making informed decisions regarding the development of future battery materials or catalysts. To support our channel's growth and ensure broader awareness, kindly hit the like, share, and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.